Nanotechnology is a word that exploded on the scene probably at around 2000. I think what was new was that there was a focus of attention for everyone in every discipline in science in looking at the prospects and properties of materials at the scale between atoms and microns. In my own field, what I'm looking at in terms of being able to make optical devices that are far more efficient than anything that we've ever had. And in particular, my research has evolved to try and understand what happens to light when we confine light into kinds of structures that we engineer, and those structures are at dimensions of less than the wavelength of light.
I'm working in a project that developing a ultra-sensitive and high-throughput sensor for disease diagnostics and food safety monitoring. So the core innovation is something called a nanoscale sensor. We can use that sensor to detect cancers, to detect viruses, to detect E. coli, to monitor the food safety issues. And the advantage of the sensor is it's very small. It's something that it's on a chip. So it's something on a fingerprint scale.
There's a lot of work in the nanophotonics arena. So we do a lot of fundamental work with light and how they interact with objects. But we do it with an application for, let's say, quantum computing or smaller circuit boards or something like that. We always try to keep an application in mind. I actually have two problems that I'm solving. One is this problem with diamonds. So diamonds are, well, everyone knows what diamonds are, but they're actually really cool outside of jewelry purposes because they have little defects, and those defects will emit light. So one of the things that we're hoping to do is take one of those defects that's really close to the surface of the diamond and kind of have that interact with another species, maybe a single molecule, and then be able to tell some very vital information about that single molecule.
We are sort of in an interesting space, kind of between very theoretical physics and very applied physics. We're somewhere in the middle. So for example, a lot of the things that we do, we're not like engineers and where we have a very particular goal in mind and we're going explicitly toward that goal, but we're also not like theoretical physicists who work on something which doesn't need to have an application at all, kind of just a study of fundamental science. What we work on is somewhere in the middle, where we try to take some interesting science, either that we came up with or that we borrowed from somewhere else, usually a combination of both, and try to do something interesting that looks like it might have potential for applications. And of course, hopefully then somebody picks that up and goes to work on it and makes an actual device.
If we look at what nanotechnology has done and what we expect of nanotechnology, actually the progress has been abundant and profound, but we no longer call it nanotechnology. Just as its roots came from many disciplines, its applications and its potential and its promise go to very many disciplines. And now we hear about the improvement in communications, the improvement in computation, the improvement in energy, the improvement in sensors. And all of that is a result of the investment and a common vision in nanotechnology.